So this is the seventh session on digital communications, and we are going to study non-uniform quantization that is used in A to D converter circuits. Now, in order to understand why it is necessary to use non-uniform quantization, we will first study the noise performance of the uniform quantization circuit. So let us start. When you are using a uniform quantizer, we have seen in our last session that signal to noise ratio, that is signal to quantization noise ratio, is given by 3L squared, where L is the number of levels that you are using. And clearly, larger the number of levels you are using, larger will be the SN ratio. And from this equation, it looks as if the magnitude of the signal does not play a role in the signal to noise ratio. However, understand that this equation was obtained by assuming that the signal has a maximum value which is equal to the absolute maximum value that is permitted by the circuit design. But if the amplitude goes below that, then the signal to noise ratio will clearly reduce. So let us use a more general equation. So again, let me repeat this. This equation assumes the signal to have peak power. Vm is equal to Vp. But when the power is low, Vm is less than Vp, then we need to use a more general equation, and that is 12 Vm squared by Q squared, where Q is the, as we discussed last time, quantization step. So clearly, if the maximum value of the signal is lower, the SN ratio is going to be low. Now for uniform quantization, Q is same. So if Vm is large, clearly SN ratio will be large. But if Vm is small, then the SN ratio will be small and the noise performance will be poor from the viewpoint of quantization noise. Okay. And the speech signal happens to be low most of the time. When we speak, generally there is a certain average level at which we are speaking, and it's only occasionally that our voice rises. So most of the time the speech signals are low, and therefore the SN ratio will be low. So in order to counteract this, what we can do is we can keep the more number of quantization levels when the signal is low and lesser number of quantization levels when the signal is high. In other words, we'll have a non-uniform step. So if we look at this waveform, now this shows two waveforms. So one waveform assumes that it has a large amplitude. So clearly you can see if the amplitude is large, SN ratio is going to be large because this is larger than the quantization step. But when the amplitude is small, it is comparable to the quantization step, and clearly the signal to noise ratio is going to be poor. Now this diagram that we are looking at corresponds to the uniform quantization step. Now in order to overcome the problem of SN ratio, we look at the next diagram which will show non-uniform quantization. So let's look at that. So you can see now when the signal is low, you got more number of quantization levels. So the quantization step when signal is low is small, and as the signal increases, the quantization step increases. So you can see that this is not the quantization step is not uniform throughout the signal levels. It is small when signal is small, and it is large when the signal is large. Okay, so this is one way of looking at the characteristics of the non-uniform quantization. But to compare, we can use another technique, plot the input-out characteristics of the quantizer and then compare uniform quantization input-output characteristics against the non-uniform. So let's do that. If you plot input on the x-axis Vi and output on the y-axis, what are we plotting? This is the quantizer characteristics. So here you can see that the quantization step is constant everywhere. It's constant. And as we said, between, say, when the signal lies between minus and minus 4 and minus 3 for this particular example. The output level is fixed at about minus 3.5, then it is fixed at minus 2.5 and so on. In any case, it is easy to see that the quantization step is uniform when you look at the input output characteristics. On the other hand, if you look at the input output characteristic of a non-uniform quantizer, then you can see that initially the quantization step is smaller, and as the signal increases, the quantization step also increases. Okay. Now, instead of actually designing a quantizer to have a non-uniform step, an alternative technique is often used, in which what is done is you use a compressor and then follow this compressor by a uniform quantizer. So what does a compressor do? It will provide higher gain for smaller signal amplitudes and lower gain for higher signal amplitudes. Once you have compressed the signal, then you can use the uniform quantizer and have the same effect. All right. So let me repeat that. You compress the signal, the compressor provides high gain for low amplitudes and low gain for high amplitudes. And then this is followed by the uniform quantizer. All right. So if you plot the input output characteristics of the compressor, how will it look like? It will look something like this. So on the x-axis you have input, on the y-axis you have the output of the compressor, and you can see that for low amplitudes the gain is larger. You can see the slope of the line is higher for low amplitudes, and this goes on decreasing as the amplitude increases, which means that the gain is less at higher amplitudes and high at lower amplitudes. And of course, just as you get this kind of curve in the first quadrant, you get in the third quadrant also, because the signal has negative as well as positive values. Now, mathematically, there are a number of equations which will give you characteristics which are similar to the compressor characteristics in general. That is, at low signal levels you can have high slope, and at high signal levels you can have low slope. You can have a number of mathematical equations. But the one which is actually used in A to D converters is a logarithmic characteristics, and that is because our ear has a logarithmic response to the amplitudes. That's why we use a logarithmic equations. So what we'll do is, first we'll develop the equation for the first quadrant and then extend it to the second quadrant, third quadrant also. All right. So the simplest equation we can start with is y equal to log of x to the base e. And if you plot this, you can write a simple program for plotting y against x for various values of x. And when you plot it, you will see that initially the gain is high, and as the signal amplitude increases, the gain falls. However, one problem with this simple equation is that it is not passing through the origin. Remember, our compressor characteristic was passing through the origin because signal will be positive as well as negative. So at x equal to 0, we want y also equal to 0. So we need to modify this equation, because here when x is equal to 1, at that time log of 1 will be 0 and y will be 0. So one simple modification for this equation you can do is y equal to log of 1 plus x. So what will happen? When x is equal to 0, you got log of 1, so y is 0 when x is 0. And then for higher values of x, when you plot y, you will get a curve something like this. Now you find that this curve, although it is having a compressor characteristic, but the gain is not very pronounced at the low values of the signal. So we need to modify this somewhat in order to provide larger gain for lower amplitudes. So what do? We multiply x by mu, where mu is greater than 1. So one characteristic that is shown here is for mu equal to 10. In fact, as you go on increasing mu, you will find that this gain will go on increasing. So right now we have a general equation y equal to log to the base e 1 plus mu x. This is passing through the origin, and we have some control over the gain through the parameter mu. If you change the parameter mu, then this low signal gain will also change. Okay. Now next what we do, we normalize this equation. So what do we mean by that? So when if we divide this by log of 1 plus mu, you will notice that when x is equal to 1, y is equal to 1. We already seen when x is equal to 0, y is equal to 0. So this is your starting point. And the ending point is when x is equal to 1, y is also equal to 1. So this is the normalized characteristics. And in order to obtain this, we have essentially divided log of 1 plus mu x by log of 1 plus mu. That is straightforward. Okay. Having done this, we can now write a more general equation where when x has a value which is x max, we want y to have some value which is y max. In general, this may be the requirement of the system. So how do we arrange that? So what we want, so this is a normalized characteristics. We want to modify this so that when x is equal to x max, y is equal to y max. So what we need to do is multiply this equation by y max, and in the numerator multiply mu by x max instead of x. So you can now see that when x is equal to x max, this is 1. So numerator is equal to denominator. So this ratio is 1 and y is equal to y max. So you have shown that when x is equal to x max, y is equal to y max, and you still get the compressor characteristics. Alright. Now for negative values, what you do? All you have to do is to attach a negative sign to the equation. So minus y max, and then here since x is negative, we take its absolute value. So mod of x divided by x max. So whether x is negative, this mod of x is going to be positive x max, and this is still is going to be equal to 1. So this is how you get the equation for negative values. And finally, you can write the entire equation y equal to y max log of 1 plus mu mod of x by x max upon log of 1 plus mu to the base e multiplied by signum x. So this signum x is plus 1 for x greater than or equal to 0 and minus 1 for x less than 0. So we had written this equation two times, one for positive values of x and the other for negative values of x. But now by using this signum function, we can express it in a single equation. And then, so we have shown here only one quadrant and shown you the result for various values of mu. So mu equal to 0, mu equal to 5, mu equal to 255. This is often the value which is used in most of the practical systems. V equal to 255 gives you good enough gain at low signal amplitudes so that you get a good signal to noise ratio overall. Now this particular law is called as a mu law, and this is used in North America and Japan. There is another law called A law, which is used in Europe and the rest. And I'll leave it to the user to discover what A law is, but basically the development of that equation is similar to this, only it is somewhat different. Okay, so in this particular session, we have studied what is non-uniform quantization, why it is required, and instead of doing non-uniform quantization, how do we use compressor followed by the uniform quantization, and also we have developed the equation for the compressor circuit. And that's all in this session.